This is the inaugural episode of Conversation with OLI experts on the science of electrolyte technology. And it's my distinct pleasure here to be with Dr. Anderko, who is the CTO of OLI Systems. He's also the lead technology visionary behind all of our products and technologies. And what's exciting to me is every time I speak with Andre, I learn something new about science and technology that inspires me. And now OLI is bringing these conversations to all of our clients and partners around the world so that you can actually benefit from some of these deep insights and glean more about understanding about the technology from Dr. Andre Anderko. And we will continue this with multiple other episodes. Today is the first episode. We'll have more talking to other OLI experts. But really, for the first episode, you have our technologist and the leader of our technology team, Dr. Andre Anderko. And my name is Vineeth. I'm responsible for the global sales, marketing, service support, and product strategy for OLI. And really, I work closely with Andre and his team. And I will be asking him a few questions today, and then we'll get his insights on the topics. The topic of the conversation today is on carbon transportation, where we'll be looking at the effect of corrosion during carbon transportation. How do we mitigate corrosion risk during carbon transportation? With that, let me turn it over to Dr. Anderko for just a quick introduction. Andre, you want to?
Thank you, Vineeth. Thank you for a kind introduction. It's my great pleasure to have a chance to talk about our technology and the newest developments that we've been putting into our software over the past few years.
Fantastic. Thank you, Andre. So can you tell us a little bit about, what is carbon transportation? Why does it matter? Who's really, working on carbon transportation? Can you please give us a little bit of context before we get into the technology itself?
Sure. As everybody knows, global warming has become a reality. Mitigating global warming is rapidly becoming a priority for industry, for governments, and for the society in general. It is now globally recognized that we need to reduce CO2 emissions to limit the global temperature rise. And one of the key paths to achieve that is through carbon capture, utilization, and storage, or CCUS, as it is often referred to. In short, we need to capture CO2 from the biggest emitters and either dispose of it in geological repositories or convert it to useful products, such as building materials. The captured CO2 needs to be transported from the capture site to the storage location through pipelines or as bulk cargo on ships or trains. And it is the CO2 transportation that is the weak link in the carbon capture and storage because it can suffer from corrosion problems.
Great. Can you tell us a little bit about, why is corrosion a concern in transportation? Is carbon dioxide actually corrosive, or is something else making it corrosive? Can you give us some insights on that?
Yeah, indeed. This is the key, because pure carbon dioxide is not corrosive. However, the reason for the possibility of corrosion is the fact that the captured CO2 is never pure. It always contains some impurities that result from prior combustion processes or just the capture processes. Such impurities include various nitrogen oxides, sulfur oxides, sometimes referred to as NOx and SOx, hydrogen sulfide, oxygen, and water. These impurities can react and form highly corrosive acids or elemental sulfur. The acids can form in minute quantities compared to the huge amounts of CO2, but they can be extremely aggressive to carbon steel and can lead to catastrophic failure of the pipelines or of tanks.
So I get it that you can have acids that can really attack carbon steel, right? That makes corrosion a problem. But why not just use some corrosion-resistant alloys with, let's say, a nickel-based alloy or something else that is designed to, withstand this corrosive attack?
Yes, this is an excellent question. The reason is economics. For a pipeline transport, the material choice has a huge impact on the cost. Corrosion-resistant alloys are expensive and can probably be used only for very short pipelines, while carbon steel is really the only economically realistic alternative for long pipelines. Corrosion-resistant alloys, which are considerably more expensive, can probably be used only at the capture site, exactly where the aggressive species are generated and where they are expected. Therefore, we are stuck with carbon steel for the transportation of CO2. And faced with this constraint, avoiding corrosion of carbon steel due to the formation of acids is really of utmost importance. The key question is, what are the safe limits for the impurities? If the concentrations of the impurities stay below the safe limits, one won't have to remove them through any cleaning procedures, which are necessarily costly.
Yeah, thanks, Andre. You put that very simply here, for somebody to understand what this is. So now can you tell me a little bit, OLI as a company, we're all about electrolytes and water chemistry. That's kind of what we do. We are a renowned leader in the world in this space. Where do electrolytes and water chemistry really fit in here? And how do you explain their impact on corrosion in carbon transportation?
Yes, indeed, electrolytes are the key. The reactions that lead to the formation of the acids and/or to the formation of elemental sulfur are necessarily electrolyte reactions. And we need to be able to predict under what conditions the impurities can react and under what conditions they will remain innocuous. And the conditions include the various combinations of impurities and their particular concentrations, as well as the pressure and temperature. So indeed, we have quite a lot of combinations which determine the reactivity. And if we can predict such conditions, then we will be able to predict the safe limits.
Great. So then, what is the science behind this? OLI has spent a lot of time thinking about the science behind the fundamental phenomena and how this works, right? So could you talk a little bit about the science behind electrolytes and how they work and how we understand that?
Sure. When you look at it, the key scientific problem is the simultaneous prediction of both reaction equilibria and phase equilibria in dense phases dominated by carbon dioxide. We have already mentioned the reactions between the impurities, which are at the core of the corrosion problems. But phase equilibria are equally important because the acids will be corrosive only if they form as a separate phase, possibly in the form of droplets at the bottom of the pipelines. And also elemental sulfur will be harmful only if it drops out of the carbon dioxide phase. On the other hand, if the acids remain dissolved in the bulk CO2 phase, they can follow the stream without affecting the transportation pipeline. Therefore, the threshold for the formation of a separate acid-rich phase, or in other words, when the solubility limit is exceeded, needs to be known for a wide range of pressures and temperatures that are relevant to CO2 transport systems.
Great. So I can see now how OLI plays in this space with our modeling and simulation solutions. So can you talk a little bit about what OLI's solution is and how we can help to address this problem?
Yes, OLI has joined forces with the Norwegian Institute for Energy Technology, or IFE in short, to develop a methodology for predicting when the impurities will pose a danger to the integrity of the CO2 transportation facilities. We are currently in the middle of a 6-year research effort, co-funded by the Norwegian Research Council and a consortium of 6 oil and gas and metal manufacturing companies. IFE is drawing on its world-leading experimental facilities to investigate the chemical and phase behavior of impurities in CO2. And OLI is combining its expertise in electrolyte thermodynamics with the experimental data that are being generated at IFE to develop an accurate thermodynamic model for predicting the formation of corrosive components.
Excellent. And what would be the components of OLI solution as our clients think about what can they use from OLI to practically solve their problem?
The key enabling technology that we are using here is OLI's mixed solvent electrolyte model, which is already quite well known to the clients who use our software. This model is the most appropriate framework for predicting both chemical and phase equilibria in CO2-dominated environments. This is due to the fact that the MSC model combines the standard state properties of both electrolyte and non-electrolyte species with an excess Gibbs energy model that allows us to span the whole range of conditions from aqueous to non-aqueous solutions. And that is really the key. MSC offers a unique modeling tool because while electrolyte reactions in aqueous systems are well known, those in dense CO2 environments are still really at the frontier of electrolyte thermodynamics. The MSC model is implemented in the OLI software, including the OLI Analyzer Studio and OLI Flowsheet. And while this work on reactivity in CO2 transportation is still in progress, we have already demonstrated that our predictions are in a good agreement with the data that have been measured so far. And ultimately, after the experimental program is completed, we intend to use the model to generate guidelines for the acceptable levels of impurities in CO2 transportation through the use of the model in our software.
That sounds very exciting, Andre, to understand what we're doing, how we're furthering this technology. Are there any other tools that clients can or interested prospects can look at to learn more or see what we've done in terms of articles or papers in this technology?
Yes, indeed. We have recently published a paper jointly with our IFE partners. The paper has been published in Industrial and Engineering Chemistry at the very end of 2019. And we would like to invite you to look at that paper. The detailed reference will be given in our recording and on our website. And there is also another paper published by IFE, which provides a very good background of the corrosivity effects of impurities. And it's been published in Corrosion also in 2019. And whenever you have questions about the papers or the technology in general, or about the application of our software in this area, please contact us for further information.
Excellent. No, thank you so much, Andre. This has been a real pleasure to get your insights on carbon transportation and why mitigating corrosion is definitely an important element of the design of those processes and the operations as well. So thank you very much. And to our listeners, thank you for listening in. We will come back to you again till the next episode in 2 weeks' time. And thank you again, Andre.
Thank you, Vineeth.